Have you ever looked at yourself in a mirror and simply wondered why you see yourself at all? Not just in the sense of the image, but in the deeper sense of physics. Why does light, when it hits a surface, decide to come back toward you instead of disappearing somewhere into the void? At first glance, it seems trivial. Mirrors are shiny, smooth, and reflective. But what happens in that tiny instant when a photon, a particle of light, barely more than a flicker of energy, meets the electrons of a reflective surface? How does it know to reverse direction and carry the image of yourself, or the room, or the sky back to your eyes? These are the questions that make ordinary things extraordinary when you pause and think about them. They are not just curiosities. They are the very principles that tell us how the universe communicates its structure through light. To begin with, we need to consider what light actually is. Light is not just a beam that travels from one point to another. It is an intricate dance of electric and magnetic fields that oscillate in a synchronized manner, propagating through space. We often talk about photons as if they are tiny particles, because they behave like particles in some experiments. But they also behave like waves. This dual nature is one of the most fundamental concepts in physics. The wave describes the probability of where a photon might be, and when it interacts with matter, it shows the particle characteristics. It hits, it transfers energy, it reflects, it refracts. It is this duality that allows light to reflect back so consistently and yet unpredictably when conditions change. When a beam of light encounters a surface, it does not just bounce like a ball. Instead, it interacts with the electrons and the atoms of that surface. Electrons are charged particles, and light is an electromagnetic wave. When the oscillating electric field of the light hits the electrons, it exerts a tiny force on them, causing them to move. These electrons then become tiny antennas that emit their own electromagnetic waves. It is this re-emission of waves by the electrons that we perceive as reflection. And remarkably, this emission is not random. The electrons collectively organize the reflected wave in such a way that it travels back in a direction determined by the angle of incidence, the same angle at which it arrived. The simplicity of the angle of incidence equals angle of reflection hides an incredibly complex interaction at the quantum level. The nature of the surface also matters. If the surface is smooth at a microscopic scale, like glass or polished metal, the re-emitted waves are coherent and orderly, giving a clear reflection. If the surface is rough, like concrete or sandpaper, the waves scatter in many directions, which is why you see a diffuse reflection instead of a mirror image. This simple observation connects to a broader idea. The universe is orderly, but the level of order determines the patterns we see. Reflection is a perfect example of how microscopic behavior, the electron's response to light, produces macroscopic phenomena we experience daily. The entire process is deterministic and yet elegant, as if nature has an economy of actions, a tiny interaction leading to a large-scale predictable outcome. If we dig deeper, the laws of quantum electrodynamics, the theory describing how light and matter interact, give us an even more fascinating picture. Every photon approaching a surface can be thought of as exploring all possible paths it could take. This sounds strange because we normally think of photons traveling in straight lines. But in quantum theory, each possible path contributes to the probability of where the photon will actually end up. Remarkably, the paths interfere with each other, and the most probable path, the one with constructive interference, is exactly the path dictated by the classical law of reflection. In other words, even the strange quantum behavior of light produces a result that matches what our everyday intuition and classical physics tell us. This is a subtle reminder that nature's complexity often reduces to simple patterns when we observe it at the scale we live in. Now consider the role of energy in reflection. When light hits a surface, the energy carried by the photons is not lost. The electrons absorb this energy briefly, oscillate, and then re-emit the energy as new photons. In a perfect mirror, almost all the energy is reflected, with very little absorbed or converted to heat. In other materials, some energy is absorbed, which is why darker surfaces appear dimmer. They trap more light as heat. This interplay between absorption and reflection gives us the colors we see, the brightness we perceive, and even the temperature of surfaces under sunlight. Reflection is not just about direction. It is about energy conservation, about how the universe balances forces and transfers energy seamlessly in ways we often take for granted. But reflection also has a philosophical dimension. Light returning to your eyes from a surface allows you to perceive the world, to see yourself, to interact with your surroundings. Every reflection is a messenger, a tiny courier that carries information from one point to another. When light bounces off an object, it brings back information about shape, texture, color, and distance. Without reflection, vision as we know it would not exist. The simplicity of a mirror then becomes profound. It is not just a shiny object, but a medium through which information flows, a conduit for understanding reality. The electron's tiny oscillations are the first step in a chain that allows consciousness to recognize form, to interpret signals, and to navigate the world. There is also something beautifully universal in reflection. The same rules apply whether you are looking in a bathroom mirror, observing sunlight glinting off a lake, or examining the reflection of stars on a telescope lens. The physical laws do not change. Electrons oscillate, photons travel, angles are conserved, energy is balanced. The regularity of these laws allows us to predict, to design, to create instruments that extend our vision far beyond human limitations. Reflection is not a trivial property. It is a manifestation of the consistency of nature. By studying reflection, we glimpse the underlying symmetry and order in the universe. Even the angle of reflection, the simple rule that the angle of incidence equals the angle of reflection, is not arbitrary. It emerges naturally from the principle of least action, a foundational concept in physics. Nature, in a sense, always chooses the path that requires the least effort, or more accurately, the path that minimizes a quantity called action, which combines energy and time. This principle explains not only reflection, but also the trajectories of planets, the behavior of light in lenses, and even quantum phenomena, the electrons in a reflective surface, the photons approaching them, and the resulting path of the reflected light, all conspire to obey this principle. What seems like a mundane bounce is actually a tiny echo of the universe's deep preference for efficiency and elegance. Furthermore, reflection demonstrates the interplay between determinism and probability. Classical physics tells us exactly where light will go, given the angle and the surface. Quantum physics, however, tells us that the photon explores all possibilities and then chooses the most probable path. And yet, the outcomes converge, showing that at the interface of order and randomness, there's a harmony that produces predictability. This is a lesson not just for physics, but for understanding patterns in nature more broadly. What appears random at a small scale can give rise to order at a larger scale, and reflection is a daily reminder of that principle. We can also think about the reflection from another perspective as a dialogue between light and matter. The photon carries information about its source, and the electrons respond in a way that returns part of that information. In this sense, every reflection is a conversation, a response that is constrained by laws yet full of subtle complexity. By observing reflections carefully, scientists can infer properties of surfaces, detect microscopic imperfections, and even measure phenomena that are otherwise invisible. Reflection is not passive, it is informative. It is the universe telling us something about itself quietly through the medium of light. Moreover, the study of reflection has practical implications that extend far beyond philosophy. From designing optical instruments to creating laser systems, from understanding how the human eye works to developing technologies and telecommunications, reflection is fundamental. Engineers manipulate reflective surfaces to control light paths, to concentrate energy, or to scatter light strategically. The principles we observe in a mirror are applied in fiber optics, telescopes, microscopes, and countless devices that shape modern life. What starts as a curiosity, why does light come back, becomes a tool for innovation, discovery, and progress. Reflection also connects to our perception of beauty. There is some thing aesthetically pleasing, about symmetry, about seeing a perfect mirror image, about sunlight glinting on water. And that aesthetic arises from the same physics that governs every photon's interaction with electrons. The laws of nature do not distinguish between utility and beauty. They produce both simultaneously. When we marvel at a reflection in a lake or a polished surface, we are unknowingly appreciating a manifestation of electromagnetic interactions, of wave interference, of energy transfer, all perfectly consistent with fundamental principles. Science and aesthetics converge in reflection. At the microscopic level, the electron's response to light can be modeled with oscillators, like tiny springs that vibrate when disturbed. This simple model captures much of the behavior of reflection, absorption, and even the slight color variations in materials. These oscillators are governed by fundamental constants, by charge and mass, by the strength of electromagnetic interaction. In every mirror, in every reflective surface, countless electrons follow these rules, each acting locally yet producing a coherent global effect. It is remarkable that the collective behavior of innumerable microscopic entities produces such predictable macroscopic results. Imagine for a moment that you are standing in a dark room and someone suddenly shines a beam of light across the space. You watch as it hits a surface and reflects back, illuminating part of the room you could not see before. It seems so ordinary, so effortless that we hardly give it a thought. And yet, what just happened is a remarkable event, a tiny performance of the universe's laws, occurring billions of times per second in every corner of the cosmos. Every photon in that beam of light is on a journey, encountering obstacles, responding to forces, and eventually returning to your eyes. Reflection, as simple as it seems, is a dance between light and matter, a choreography dictated by the fundamental interactions that govern everything from atoms to galaxies. To understand this, we must start at the level of the photon. Light is not merely a stream of energy, it is an entity that carries both energy and momentum, a particle and a wave simultaneously. When a photon encounters a surface, it does not blindly bounce back as a ball might. Instead, it interacts with the charged particles in the material, primarily electrons, exchanging energy and momentum. The electrons respond to the oscillating electric field of the incoming light, moving slightly, and in turn, they radiate new electromagnetic waves. The wave that we observe as reflected light is a coherent sum of countless tiny emissions from these electrons, all aligning in such a way that the resulting wave travels away at an angle precisely dictated by the law of reflection. This process is astonishing in its precision, microscopic chaos producing macroscopic order. One of the most fascinating aspects of reflection is how it reveals the dual nature of light. In some experiments, light behaves like a wave, creating interference patterns, bending around corners, or spreading through tiny apertures. In other experiments, it behaves like a particle, delivering discrete packets of energy when it interacts with matter. Reflection is one of those phenomena that bridges both perspectives. Classically, we can describe it using rays, angles, and predictable paths. Quantum mechanically, each photon explores a myriad of possible paths, and through constructive interference, the most probable path emerges, the one that obeys the classical law of reflection. In this sense, reflection is both simple and profound, a tangible manifestation of the universe's hidden complexities. Consider now the role of the surface itself. Not all surfaces reflect light equally. A perfectly polished mirror will send almost every photon back along a precise path, creating a clear image. A rough wall scatters light in multiple directions, producing a diffuse reflection that reveals the general shape of the wall, but not detailed features. At the microscopic level, this difference arises from the arrangement of atoms and electrons on the surface. Smooth surfaces ensure that the re-emitted waves from electrons remain coherent, while rough surfaces introduce phase differences that lead to scattering. In both cases, the underlying physics is the same: the interaction between electromagnetic waves and charged particles. What changes is the structure of the material, which dictates the pattern of the reflected light. This teaches us a valuable lesson: order and structure in Nature determined the clarity and quality of the signals we receive. Reflection is also intimately tied to the conservation of energy. When light strikes a surface, the energy of the photons is redistributed. Some of it may be absorbed by the material, slightly heating it. Some may be transmitted, passing through if the material is transparent. The portion that is reflected carries the same energy back into space, preserving the total balance. In mirrors and highly reflective metals, nearly all the incident energy is redirected, which is why they appear bright and shiny. This conservation is not a trivial fact. It is a cornerstone of physics, echoing across mechanics, thermodynamics, and quantum theory. Every reflection is a testament to the universe's meticulous bookkeeping. There is also the intriguing phenomenon of polarization, which adds another layer of complexity. When light reflects off a surface at certain angles, its oscillations become aligned in specific directions. This is why polarized sunglasses reduce glare. They block light waves that have been preferentially reflected from horizontal surfaces. Polarization demonstrates that reflection is not just about direction, it is about the character of light itself. The universe is capable of transferring subtle properties through interactions that we often ignore, yet these properties influence the way we see, perceive, and interact with the world. Reflection, therefore, is a messenger carrying both obvious and hidden information. As we move into the quantum domain, reflection becomes even more astonishing. Each photon can be thought of as exploring every possible path it could take, a concept known as the path in integral formulation. The photon's probability to arrive at a certain point is determined by summing over all these paths, with interference enhancing the paths that correspond to classical reflection and canceling out the others. What appears to be a simple bounce of light is, in fact, the outcome of countless quantum possibilities, all interfering to produce a single predictable result. The universe is, in essence, computing these probabilities for every photon, every moment. Reflection is therefore not merely a physical event, it is an expression of nature's underlying computational elegance. Reflection is not only a physical phenomenon, but also a source of information. When light bounces off an object and returns to your eyes, it carries with it details about shape, texture, distance, and color. Mirrors and reflective surfaces allow us to perceive the world, to navigate, to interact, and even to contemplate ourselves. The electron's tiny vibrations translate into the macroscopic reality we experience. In this way, reflection is both a messenger and a translator, converting microscopic activity into perceptible phenomena. The world we see is a continuous dialogue between light and matter, mediated through countless reflections, each contributing to our understanding of reality. One of the most striking aspects of reflection is its universality. The same laws govern a mirror in your bathroom, the glint of sunlight on a lake, and the reflection of stars in a telescope lens. The behavior of photons and electrons does not change based on context. It is consistent, predictable, and reliable. This universality is what allows science to flourish. By observing reflection, we can design optical instruments, create communication systems, and explore distant galaxies. What begins as a simple curiosity, why does light come back, becomes a foundation for knowledge, technology, and discovery. The humble act of reflection is a gateway to understanding the order of the cosmos. We can also explore reflection from a practical standpoint. Engineers and scientists manipulate reflective surfaces to control light, concentrate energy, and detect subtle signals. Lasers rely on precise reflections between mirrors to amplify light. Fiber optics use total internal reflection to guide information across continents. Telescopes and microscopes exploit reflection to extend our vision far beyond the capabilities of the naked eye. Reflection is not just a curiosity, it is a tool, a principle applied in countless technologies that shape modern life. The simple question, why does light reflect, leads to innovations that affect everything from medicine to communication to space exploration. Reflection also has profound implications for our understanding of symmetry and conservation laws. The predictable behavior of light upon reflection is a consequence of deeper symmetries in nature, particularly those that govern energy and momentum. When a photon reflects, the total momentum of the system is conserved. The photon and the surface exchange infinitesimal amounts of momentum to maintain balance. These symmetries extend across physics, explaining phenomena from the stability of atoms to the motion of planets. Reflection, therefore, is not merely about light. It is a window into the fundamental order and balance of the universe. Philosophically, reflection invites contemplati on about perception and reality. The light that returns to our eyes is shaped by the material world it encounters, yet it carries information that allows us to reconstruct that world in our minds. Our perception of reality is built on countless reflections, not just in mirrors, but in the interaction of light with every object around us. Each reflection is a tiny act of translation, converting microscopic interactions into macroscopic understanding. The clarity or distortion of a reflection tells us something about the surface, the angle, and the nature of light itself. Reflection, then, is both a physical and epistemological process, a means of knowing the universe through observation. Even at the microscopic level, reflection demonstrates the harmony between simplicity and complexity. Electrons respond locally to incoming light, obeying Maxwell's equations and quantum mechanics. Yet the collective result is a coherent, reflected wave that can form clear images, illuminate spaces, or guide laser beams. This emergence of order from the collective behavior of simple entities is a recurring theme in nature. Reflection reminds us that the universe operates through layers, simple rules at the micro level, producing rich, intricate patterns at the macro level. Observing a reflection is therefore an encounter with nature's layered design. In addition, reflection is intimately linked with time and causality. The photons that reflect carry information from one moment to another, preserving the sequence of interactions that occurred at the surface. The path of light is a record of events, a chain of cause and effect stretching from source to observer. By studying reflections, we can infer histories, detect changes, and reconstruct events. The act of seeing is, in a sense, reading a story written in light, a story told through countless reflections, each following the immutable rules of physics. Reflection is both a temporal and spatial messenger, connecting moments and locations across the universe. Furthermore, reflection demonstrates the subtle interplay between determinism and probability. While classical physics predicts the path of light precisely, quantum mechanics introduces probabilities. Yet the emergent behavior, the coherent reflection we observe, shows that deterministic patterns can arise from probabilistic foundations. Nature balances randomness and order in every reflection, providing a tangible example of how complexity can emerge from simplicity. Reflection is therefore not only a physical phenomenon, but also a metaphor for understanding the interplay between certainty and uncertainty in the natural world.